Welcome to the podcast series for a project entitled Maintaining Financial Stability in an Era of Changing Climates and Demographics. This project is funded by the SOA CAE Grants Program. My name is Kensington. The theme of this podcast is based on a research paper, Improve Index Insurance Design and Yield Estimation using a Dynamic Factor Forecasting Approach. It is a joint work with Professor Hong Li, Professor Lisa Porch, and Professor Wenjin Zhu. There are three highlights in this research. High precision crop yield forecasting is central to effective risk management for many stakeholders, including farmers, insurers, reinsurers, and governments. From the farmer's perspective, the ability to accurately forecast crop yield before the harvest season allowed them to make decisions regarding crop sales and marketing, and risk management practices such as buying insurance policy in order to mitigate losses due to potential reduced crop production. From the perspective of insurers and governments, improved approaches to predict yield can contribute to more effective and sustainable rate making, as well as implementing more informed policies and innovative risk management strategies that can protect farmers from potentially disastrous outcomes, such as that due to extreme adverse weather. Therefore, the first objective of this research is to propose an innovative crop yield forecasting model with enhanced forecasting precision. Our proposed yield forecasting model is based on a dynamic factor approach. Using both county level and state level crop production data, the empirical results indicate the dynamic factor approach produces more accurate in-sample and out-of-sample forecasting results compared to the classical statistical models. The empirical results also support the efficiency of the new index-based insurance policy constructed from the dynamic forecasting model. This finding, in turn, greatly improves the IBI's hedge effectiveness against the agricultural production, as well as increases its practicality as an insurance policy for agriculture. The remaining of this podcast is structured as follows. First, we introduce our proposed dynamic factor crop yield forecasting model. We then describe the data and present the empirical results validating our proposed model. We conclude the podcast by presenting a new index-based insurance scheme and demonstrate its effectiveness. We now briefly describe our proposed dynamic factor model. Suppose a given state has N counties and T years of yield data on a particular crop. Our objective is to propose an effective yield forecasting model for this crop. Various model specifications for forecasting crop yields have been proposed in the literature. In this paper, we consider two types of model specifications: the cross-section specification and time series specification. The cross-section specification studies the average relationship between the crop yields and the explanatory variable across multiple locations. From the display equation, the subscript I denote county and the subscript AVG emphasizes the variable are averaged over time. Hence, the notation Y refer to the county level time average crop yield for county I. The variable A is the intercept, gamma is a vector of coefficient of K dimension, X is a vector of explanatory variable, and epsilon are the IID normal residuals. An advantage of the cross-section model is that spatially varying but time invariant variables such as soil quality measurement can be incorporated, and these may provide additional explanatory power for modeling crop yields. For the time series specification, the model focuses on the dynamic relationship between crop yields and the explanatory variable for a given location, such as farm, county, or states. For this reason, we explore the time series specification at both the county level and the state level. The notation are defined similarly as in the cross-section model, However, the time series model has an additional term reflecting the time trend of crop yield. We now have 3 candidate models for modeling crop yields. The challenge with directly implementing this model is that the dimension K for cross-section specification and the dimension J for time series specification can be very large in practice. This is especially problematic for modeling crop yields due to data scarcity. To resolve this issue, we propose to use dynamic factor analysis to achieve an efficient dimension reduction. In particular, our solution involves 2 steps. In step 1, a set of latent factor is first estimated through PCA. And in step 2, a dynamic factor procedure is used to select key factors that are important for yield forecasting. Empirical results to be presented shortly demonstrate the effectiveness of our proposed dynamic factor approach at identifying key factor and dimension reduction. We next provide a brief description on the data. Our empirical study uses the following 3 types of data. The first type of data is the weather data, including the monthly average temperature and the monthly cumulative precipitation. These data are obtained from the PRISM climate group. Given the importance of soil, our model exploits soil data by incorporating 56 of the relevant soil variables. The last type of data is the crop data. Here, we consider corn, soybean, and winter wheat yield data over the period from 1981 to 2016 at both county level and state level from the state of Illinois in the United States. We chose these 3 crops because in aggregates, they account for more than 80% of the cropland in the Illinois states. The graph displays the number of acres harvested for each crop type as a percentage of the total harvested cropland. Note that the northern part of the Illinois states mainly produces corn, while the soybean and winter wheat are mainly grown in the southern part of the states. While we have weather data for the entire year, it is common to only consider the growing season weather variables in the forecasting models in view of their critical effect on the crop production. The growing season for each of the crop types is shown on the table. For example, the growing season for both corn and soybean are from May to August. Hence, the weather variable over these months are only used in the models. Before presenting the empirical results, it is useful to briefly describe the model we are comparing and the measure used to assess their relative efficiency. For comparison, we consider 3 types of models. For each model under consideration, we in turn implemented 3 specifications, namely the cross-section specification at the county level and the time series specification at both the county and the state level. The model labeled optimal factor corresponds to our proposed yield forecasting model with optimal dimension reduction via the dynamic factor approach. The benchmark regression model is the standard regression approach commonly used for yield forecasting. This model has the advantage of simplicity and parsimony. For example, with the time series specification, it involves 2 regressors, which are the average temperature and the total precipitation over the growing season. For cross-section model, it has 4 regressors, including 2 quadratic terms. Because of its popularity, this model serves as a benchmark against the proposed dynamic factor model. Finally, the model labeled constraint factor is similar to the dynamic factor model, except that the number of factors is restricted to 2 for the time series specification and 4 for the cross-section specification. These values are chosen so that the constraint model have the same number of regressors as the respective benchmark regression models. This provides us with a fair comparison so that both benchmark regression model and the constraint model have the same number of regressors. In this aspect, the constraint model is suboptimal to the respective optimal factor model. To gauge their relative efficiency, we consider two quantitative measures. The first measure is the adjusted R-square, which is a statistical measure capturing how well the model fit the data. The second measure is based on the crop validation, which evaluates the out-of-sample forecasting capability of the models. We now evaluate the model by comparing their adjusted R-square. Note that the county-level time series model are fitted to all counties within the states, and hence the reported value should be interpreted as the averages across all counties. The effectiveness of the proposed dynamic factor model is clearly demonstrated by the much higher values of the adjusted R-square as compared to the corresponding value from the benchmark regression models. Recall that our dynamic factor model exploits dimension reduction. The effectiveness of dimension reduction can be seen from the last column of the table. The optimal dimension ranges from as high as 13 to as low as 3. This compares favorably to the original dimension, which is as high as 116. As the constraint model is a suboptimal implementation of the dynamic factor model, it is not surprising to see there is a loss of efficiency as exemplified by the slightly lower adjusted R-square relative to the optimal factor model. Nevertheless, it is reassuring that the constraint model still outperformed the respective benchmark regression model. The adjusted R-square focuses on the in-sample fitness. We now test the model's out-of-sample forecasting ability. To achieve this, we use the leave one out cross-validation approach and compute the root mean square error. Hence, the smaller the root mean square error, the more efficient the underlying model is in forecasting out-of-sample use. The cross-validation results similarly confirm the effectiveness of the proposed dynamic factor model for out-of-sample yield forecasting. For example, if we were to use state specification model to predict corn yield, the benchmark regression model results in 2.5% root mean square error. The suboptimal implementation of the dynamic factor model leads to a slightly lower root mean square error of 2.2%, while the optimal dynamic factor model produces an impressive small root mean square error of only 0.9%. We now proceed to the last part of the podcast, which focuses on an application to index-based insurance. Let us first recall the main purpose of the crop insurance is to compensate farmer when there is a loss due to low crop production. For example, from the display insurance payout formula of a generic crop insurance design, YT is a random variable that relates in some ways to the crop yield of the insured crop, and K is a predetermined constant. In practice, K is typically defined as the product of the coverage percentage and the expected crop yield. Hence, K in this case can be interpreted as the minimum crop yield the farmer wishes to insure. If YT for the insured year turns out to be larger than K, then there is no payout from the insurance since the realized crop yield for the year exceeds the minimum. However, if YT is lower than K, then the farmer will be indemnified for the shortfall adjusted by the insured acres of farmland and the unit price of the insured crop. Broadly speaking, the crop insurance can be classified into indemnity-based or index-based. By indemnity-based, the payout of the insurance contract ties directly to the actual yield of the insured crop. That is, YT corresponds to the farmer's actual yield of the insured crop. The popular MPCI is an example of indemnity-based insurance. Such design has the advantage that the payout of the insurance ties directly to the farmer's actual loss. If, on the other hand, YT is linked to some external reference index, such as some well-defined weather variables, then the resulting contract is known as the index-based insurance policy. From the cost of underwriting, issuing, servicing, and maintaining the contract, IBI policy tends to have lower costs relative to the indemnity-based insurance. Furthermore, the reference index is typically selected so that it is external, transparent, and cannot be easily manipulated by all stakeholders. This feature, in turn, leads to lower moral hazard and anti-selection. Despite the advantages, the key concern with IBI is the basis risk, which is a mismatch between the farmer's actual loss and the indemnity from the IBI policy. This issue arises because the chosen reference index does not perfectly capture the farmer's actual crop yield. Hence, IBI with large basis risk will not be an effective coverage at providing necessary insurance protection for the farmers. The presence of basis risk remains a challenging issue in the design of an effective IBI. This is also a key reason why the demand for IBI remains relatively low in the agriculture sector. In this podcast, we have provided some encouraging evidence on the effectiveness of our proposed yield forecasting model based on the dynamic factor approach. Given its efficiency, here we propose a new IBI where the reference index is given by a proposed dynamic factor model. To validate our new IBI, we compare it with another IBI constructed with the reference index based on the benchmark regression model. Given the importance of basis risk, here we present two approaches of quantifying basis risk. The resulting quantitative measures are defined with respect to the indemnity-based insurance. We denote the first approach as the frequency approach, since it quantified basis risk in terms of relative occurrence. Because of the mismatch between the reference index and the farmer's actual crop yield, two situations could arise. In one situation, it could happen that the IBI policy does not generate any payout despite a loss had incurred on the farm. We denote such a scenario as type 1 error. In another situation, it could happen that the farmer actually received a payout from the IBI policy despite no loss on the farm. This scenario is described as type 2 error. If the frequency of type 1 error is large, then it is problematic to the farmer since the IBI fails to provide a much needed protection to the farmers. If the type 2 error happens frequently, then it raises sustainability issue for the insurance providers since the policy keeps paying farmers even though there is no loss. In summary, both of these errors are not desirable. An effective IBI should have this error as small as possible. To provide a greater insight into type 1 and type 2 errors, let us now illustrate this error graphically. Suppose the horizontal axis gives the actual yield incurred by the farmer. Let alpha be the deductible of an indemnity-based insurance so that if the actual yield loss is higher than alpha, then there is a positive payout compensating farmer for the loss in excess of alpha. On the other hand, if the actual yield loss is less than alpha, there is no payout to the farmer since the incurred loss, if any, is still within the farmer's loss tolerance. Suppose now the vertical axis corresponds to the value of the reference index for the IBI. Let beta represent the deductible for the IBI policy so that it generates a positive payout only if the value of the reference index is higher than beta. Hence, this graph demonstrates the relationship between the farmer's actual yield loss and the reference index. By design, the area shaded red represents the situation for which the loss incurred by the farmer is sufficiently severe to trigger a payout from the indemnity-based insurance. In contrast, there will not be any payout from the IBI policy since the reference index on the shaded red region is smaller than beta. This situation therefore corresponds to the type 1 error we previously described. Using similar arguments, it is easy to see that the area shaded yellow captured the type 2 error. Therefore, the magnitude of basis risk in terms of type 1 and type 2 error depend on the size of the red and yellow regions. The area shaded green represents the region for which the U loss is less than alpha, and the reference index is also less than beta. Hence, both design lead to the same decision that there is no payouts. The blue region also represents another situation for which both designs have the same consistent decision, except that both policies lead to positive payouts. While having positive payouts from both designs is a good starting point, the actual size of the indemnity payments is of greater relevance to the farmers. Relative to the indemnity-based insurance, IBI can actually overcompensate or undercompensate the farmer for the incurred excess loss. This insight suggests that in addition to comparing the proportion as in type 1 and type 2 errors, comparing the discrepancy between the actual payment from both the indemnity-based and index-based insurance is important as well. Hence, this leads to another measure of basis risk based on the severity approach. The table compared the relative efficiency of both IBI policies constructed based on the proposed dynamic factor model and the benchmark regression model. We apply IBI to corn, soybean, and winter wheat, and we assess basis risk by reporting quantitative measure calculated from both frequency and severity approaches. It is reassuring that regardless of which quantitative measure we adopt, the IBI based on the dynamic factor model outperformed the corresponding IBI from the benchmark regression model. In some best cases, we even have 0 type 1 and type 2 error for the corn IBI. This result compares favorably to the benchmark regression-based IBI, which produces 33.3% and 26.67% of error, respectively. To conclude this podcast, we draw the following 4 remarks. First, this paper investigates a new approach to forecasting crop yields using a dynamic factor model and proposes a weather index-based insurance policy based on the resulting model. Second, a dataset consisting of county-level and state-level annual crop production experience for corn, soybean, and winter wheat from the state of Illinois is utilized for the empirical analysis. Third, empirical result indicates the dynamic factor model developed in this paper is able to substantially improve crop yield forecasting relative to the classical regression specifications. Fourth and final remark, the resulting weather index-based insurance policy is effective at reducing basis risk as demonstrated empirically. This concludes our podcast, and thank you for listening. Goodbye.